Swayam Prabha. Digital India. Educated India.
So we mentioned that we need a time resolution in order to observe various molecular structures along this reaction path, right, as reactants go to products. And then this is the time resolution that we needed, 1 picosecond. Yeah. Suppose if I want to observe this transition state, because chemists have been long fascinated by the existence of transition state, and then it's the heart of chemical reaction dynamics, right? I mean, in the sense that without transition state concept, you won't talk about reactants going to products. But all the chemists were not sure whether such a structure exists. It only kind of predicted, okay, until 1990, okay. But we understood that we needed a picosecond time resolution in order to make a movie of these geometries. One of them turns out to be a transition state structure at some point of time, right? So if we can identify a camera with a shutter speed of, let's say, less than 10 power minus 12 seconds, we can indeed map what is the possible transition state structure, right, at some point of time, because reactants take some time to reach here, and then if you keep mapping them, and then this camera happens to be the laser pulse, okay, because we can't see with our naked eye these transformations to products, right? Okay. Yeah. So we talked about laser pulse. We talked about the wave packets, the nuclear wave packets evolving on electronic potential energy surfaces with obeying this equation, right? And then we brought in the fact that there is a laser pulse which can actually monitors the evolution of this nuclear wave packet, because as the nuclear wave packet evolves on these potential energy surfaces, this is actually a potential energy surface, right? I only draw it in one dimensional card. As it evolves on the potential energy surfaces, the laser pulse can track its motion, because this is the camera that we have. So the nuclear wave packet kind of representing this configuration. So the laser pulse clicks a picture suddenly, clicks this picture, and then make a movie out of it, okay? And then why does it, how does it do? How does it do? And this should be, since we are talking about a camera, that should be less than 10 power minus 12 seconds with a shutter speed of less than 2. So I call it femtosecond laser pulse, okay? Because laser pulse are kind of characterized with their time duration, okay? So if the pulse is of the order of 10 power minus 15 second duration, then I call femtosecond pulse, okay? Okay, with these kinds of pulses, we can track the motion of the reactants as they go to products, and then with a hope that we can locate the transition state, right? That was the initial endeavors from chemists, that locating transition state was kind of very hard, because it's a very fleeting, right, object, because it's very transient in the sense it only exists, let's say within this region, not even 10 angstroms, within this short region, which is around, let's say, 1 angstrom, of the order of 1 angstrom, okay? You would need much more shorter laser pulse to probe that, okay? Just following the same arguments with, if it's, so molecule gets slowed down as it reaches the transition state. The speed would be, you imagine that it's around 1 kilometer per second, because it's an average motion that we took, the velocity we took. So, and then you can kind of confine it to this 1 angstrom and then see the time scale associated with tracking this transition state. Okay, it's even lesser. So therefore, people could not perform any experiment, because there weren't lasers available until 1960, and then after that, once the lasers are in place, people exploited it for every let's say 3 orders of magnitude down in time. 10, in other words, 10 power minus 3 to 10 power minus 16. Okay, the latest development in this field is generating attosecond laser pulses. Okay, there is something called, you would have to use mode locking to generate laser pulses. Okay, so you have a laser system, you have to generate these short time laser pulses. You would have to do that with mode locking, but that's just that's just something that you can look into it. Okay, it's all more physics of laser physics and all. Okay, so once we have our tool, so our tool to observe the reaction dynamics, this is called reaction dynamics, because I'm kind of seeing how the reactants evolve into products in time. That's why it's called reaction dynamics, right? So you kind of can see then we have a tool to probe that such a reaction, which is laser pulse, yeah, femtosecond laser pulse. And then what did Zivale do? So you can see, I mean, sample femtosecond laser pulse here, right? I mean, just pictorially, before getting into Zivale's experiment. You see here, you have a laser pulse exciting the nuclear wave packet here to the states here. Okay, so I mean, it mainly targeted this one. But what happens, a femtosecond laser pulse is something which I draw it schematically this way. Okay, so it's time versus femtoseconds, the electric field amplitude. Okay, E naught, electric field amplitude. You can mathematically represent that like it's a sinusoidal wave, some sinusoidal wave with some carrier frequency multiplied by some Gaussian function, right? You can just mathematically represent it's something like this. So you can kind of E naught, sorry, this is E of t. T e power minus t by tau square, yeah, tau square, something like this. You can represent this way. It has a carrier frequency, it has some amplitude. Okay, these are the important aspects of laser pulse. The carrier frequency, that means the frequency with which the resultant wave oscillates, and you have the amplitude. At this time this is amplitude, at this time this is amplitude. So for different times the amplitude varies. Okay, so that's a laser pulse. So you have a start time, you have an end time, and then this is like the duration, the delta t I call, okay, between these of the order of femtoseconds, 50, 20, 100 femtoseconds, things like this. Okay, so by Fourier theorem, if you kind of compress an object in time, you would have, I mean, the object kind of expands in frequency domain. You heard about this, right? Yeah. Suppose if you Fourier transform this function, there is something called there is some mathematical technique called Fourier transformation. So you have a time dependent function, you put it in that Fourier winding machine, and then kind of that machine throws out the following thing. You can kind of get for this curve, okay, it just gives you its frequency spectrum. That means how many frequencies are actually in there. It's not just one frequency as you see here. Okay, the fact that you are actually getting a localized wave of this form to represent your laser pulse means that you are kind of combining several waves with different frequencies and then trying to see construct interference in one localized region and restrict interference everywhere else. Okay, that's what you are doing. Maybe just to give you an illustration. Suppose if I add sine wave, right, with some frequency, let's say sine omega 1t, okay. This is sine 2 omega 1t, okay. And then similarly I go this sine 3 omega t, and so on. I add the net resultant of these waves is going to be something like this, right? You can try this in any graphical tool. You can just, there is something called Desmos. You just add different sine curves with different frequencies. You kind of tend to see a behavior. Say a localized wave in certain region and the other region it gets. Okay, that means you have, so what this Fourier winding machine does, it kind of brings out all these frequencies, omega 1, 2 omega 1, 3 omega 1, which are actually involved in the formation of this wave, I mean a kind of laser pulse here, right. So all these frequencies are brought in here, omega 1, 2 omega 1, 3 omega 1 and whatever, okay. So this is just a carrier frequency, in the sense it's kind of the omega that you are writing here is a net resultant frequency of this wave, okay, this wave. So this omega will be somewhere here and there is some omega minus delta, omega plus delta, in which all these other frequencies fall, okay. Okay, so good. So you have, so that means the fact that you are applying a short laser pulse, you're actually coming up with a lot of frequencies in it, right? If these frequencies correspond to, let's say you have a short laser pulse here, it has many frequencies in it. So it can, I mean there is a frequency component that can actually see this. If the spacing between these levels is such that the laser pulse can also cover this frequency because of its shortness in time, okay, then it also brings in this excitation. This state is also brought in this excitation. So if the laser pulse, if it can span all the frequency components here, there is a frequency here, there is a frequency here, there is a frequency here, right? If all of these frequencies, if you design a laser pulse such that all these frequencies are encompassed in that laser pulse, so in other words, this particular state of the molecule is promoted to all these states simultaneously, okay, and mathematically that is simply represented as this one. You see here the state 1, state 2, state 3 in sigma, and then each of these states are kind of partly populated with their coefficients A1, A2, A3, okay. And then this is what we call wave packet, okay. And this is the object of interest. The nuclear wave packet that you had seen is actually a superposition of all such states created by the laser pulse, okay. And such a wave packet is guaranteed to give you all time dependent phenomena of interest to molecules. For instance, if you take only this component, and then if I just only put my molecule into completely this state, yeah, forget about all, I mean I design a laser pulse such that it only has one frequency component and prepares only this state. The entire molecule is simply put it in here rather than encompassing all these states, okay. If that is the case, I would ask you to simply calculate what is the probability density of this molecule to be found in this state at all times. So you would simply take this wave function and then try to do its square, right? That's what is the probability. So when you do that, you get psi 1 square, that's all. The phase factors cancel out, right? you have psi, I mean, how do you do this square? It's a mod psi square, which means the modulus of e power minus IET by h is 1. Yeah, it's an oscillatory phase factor with the modulus being 1. Or in other words, you can also just see that you see here you have a wave function. This is the space part, this is the time part. Actually it actually is a solution of this equation, okay, a particular solution of this equation. So what would happen if I take mod psi square? That means let you call it psi. So it's psi star psi, no? If you put psi star, this becomes plus psi, and there is psi which is minus I. They cancel each other, and you get finally psi 1 x square, right? That's what you get. So if you prepare such a state of the system, you would have no time dependence in the probability density. That means all other observables which you can calculate out of this wave function turn out to be time independent. But we are kind of clearly seeing that reactants are evolving into products. So this will not be the right description for reaction dynamics, okay? Preparing one single state is not the right description to have the time dependent dynamics, okay? Time dependence in the system. So therefore, laser pulses aid us preparing a wave packet, okay? So of this sort. For instance, you take let's say two states you take, okay? Just what wave packet does, you take two states, E and E prime with their energies e power minus IE prime t by h cross E, linear combination of two states. And then you square it, this is your wave function, you do modulus of psi x t square, psi star psi for this wave function. So these are time independent portions here, but the magic is here. There is a portion which is dependent on time, which is actually, you see here, the probability density is dependent on time. It's oscillatory. It's kind of, sometimes this portion is added to this portion, making it bigger. Sometimes this portion actually getting subtracted from the, because you have e power minus IET sitting here, no? What does that mean? What is e power I, formula for e power I theta? Cos theta plus I sin theta. So you have real and imaginary parts that are actually oscillatory, positive, negative, right? Cos theta, how do you, minus 1 to plus 1, it oscillates, no? It's an oscillatory function. So it's sometimes when it is positive, it adds up, sometimes when it is negative. I mean, you can kind of finally, you can also, so I'm saying here, real part of this quantity. What is the real part of e power I theta? Cos theta. You get cos theta, cos of e prime minus e, the energy difference between these two states. So with that beating, you have the probability density oscillating in time, okay, when you have wave packet. If you have three states, it becomes much more complicated. You have many beatings in it, okay. If you have four states, you have pairwise, let's say E1 minus E2, E3 minus E4, and different cos terms and things like this, many beatings. So that's how the time dependent phenomena in molecules are described, by creating a wave packet with laser pulses, or by tracking this wave packet after creation with laser pulses, okay. Okay, fine. For instance, you see there is a laser pulse which actually can span all these states. The frequency content of this laser pulse can span all these states here. You see here, I want to excite the molecular system here, from here to this state, this excited electronic state with these many because each electronic state, remember, has vibrational states in it, right? This is an electronic state, ground electronic state. So whenever I say hereafter, or somebody says this represents an electronic state and another one represents electronic state, they are actually writing down the electronic energy as function of nuclear coordinates, as we discussed, right? It's not like electronic state is no longer like this. your electronic states are no longer like this, okay. So this is, I mean, this is only true if you have a fixed molecular structure. Let's take benzene, okay. At its equilibrium structure, these are the first electronic, second electronic, third, and you have vibrational states. But our picture now is very different, right? Because we understand that electrons and nuclei interact, and then we apply Born-Oppenheimer approximation, and then kind of deal with them separately, and then bring the interaction later. That's what we are doing. So then you kind of take one mode of the benzene and then kind of distort it, then you get a slightly different spectrum, okay. And then again you distort, you kind of get slightly different electronic state spectrum. It keeps oscillating with the nuclear geometry. So what these cuts are doing, they are kind of connecting all the ground state energies. These points they connect, they call it one surface, electronic state 1. They connect only these things and they call electronic state 2, okay. And then they connect these things, electronic state 3. Somewhere at this point these electronic states start talking to each other, okay, not at the equilibrium geometry but somewhere at the fall configuration, okay. So anyway, so but now you have a vibrational levels of each electronic state still remaining, but slightly different from this equilibrium, from the ones that are at the equilibrium configuration, okay. The spacings will be different and okay, fine. So you see here you have an electronic potential in which the molecule is sitting in the first vibrational level, and then you want to promote it to an excited electronic state, and you want to use it, use a laser pulse of this kind. So this laser pulse of this kind can span all the frequencies that can accommodate excitation to these levels, okay. That means you kind of get a coherent wave packet. When you add many sine waves, as I mentioned, you get a wave packet right here in the white, you see in the right side, yeah. Sorry, these are laser pulse, the white one is the laser pulse, okay. It can have all these frequencies in it, and then you create a wave packet of this localized wave packet. You see here, what is the difference between this wave packet, this wave function here, and then the red one here, or for that matter this wave function here, this wave function here of the excited state potential. So this is excited state electronic energy and it has its own vibration levels. These are excited vibration, that's why you have many nodes. Harmonic oscillator you are familiar with, right? So that's what we are doing. So you see here, these are delocalized, these are the eigenfunctions of the system, whereas the wave packet is highly localized. You see, what is that? It's approximately 2.4, can you read this? 2.4 to 3 angstroms, that means 0.5. The wave packet is much more localized, it's localized to 0.2 angstroms, yeah. So laser pulses on femtosecond time scale create a localized wave packet. So that is crucial to femtochemistry, okay. And these localized wave packet is not stationary. You understood? It's a non-stationary wave packet. That means it doesn't stay there, it evolves in time, okay. As it evolves in time, it kind of also spreads, because the localization will eventually spread, okay. The wave packet will eventually spread, and then the spreading, the evolution will describe different aspects of chemical bonding, okay, as illustrated by Ahmad Zivel. We'll try to see his experiments and try to understand his experiments in the context of laser pulses and wave packets, okay. By the way, the center of such a wave packet, that means somewhere here, okay, evolves like a classical particle, like in the sense, if I write it, the center, usually the expectation value of the x operator, the position operator gives you the center, okay. It actually is simply this is constant, the momentum, and with time it simply evolves like a classical particle. Okay, though the wave packet itself is a quantum mechanical concept, the center of the wave packet has an intuitive physical picture that it simply evolves like a classical particle. Okay, so that helps us to get some insights into the molecular evolution. Okay, you can think it in terms of classical particle rolling on a potential energy surface. When you have a wave packet, it's like you have a potential energy surface, it's like you have a hill, you put a wave packet and it rolls like a classical ball. Okay, only that it dephases, it kind of spreads because of the quantum mechanical behavior. Okay, okay, let's just look at the slides. So where are the slides? No, here. Okay, fine, here. Okay, so I asked you initially one question, right? Why do we need to study chemistry in real time? That means why do you want to track these chemical bonds, right? Suppose we don't want to track it, okay? We'll just see how people misconcepted the motion of, let's say, a macroscopic like object like a horse, for instance. This is like poetic imagination. Okay, it's like a poet assumes that the horse with its 4 legs moving completely stretched for, it's kind of, this is amazing. So if you don't see it through science, you assume it that's correct, right? But we'll see whether this is actually the so. Okay, the poetic artistic thing is correct. So there is a person called Edward Muybridge, okay, who took the photographs of such a moving horse in a racetrack with a camera speed of, let's say, with a camera of shutter speed of 1 millisecond. That's enough to resolve the horse movement, horse spatial resolution, let's say 1 centimeter, for instance. For every 1 centimeter, you can map the entire leg, right? So let's say if the horse is moving with 10 meters per second and you want to resolve in space 1 centimeter, that means just to map out the whole body of the horse, you want to take the resolution of 1 centimeter. Then you need a camera with a shutter speed of 1 milliseconds. Okay, the shutter has to repeatedly move back and forth with to capture it. So you see here he captured all these snapshots, keeping the camera at successive points on the racetrack, and then kind of proved the following. Can you see in all of these images which he took an image of this kind, okay, where all the legs are stretched away from each other? I just ask you. So when all the legs of this horse are kind of off the ground, they're kind of coming close together, not just moving away. You can see the second one, you can see the third one, and then how it is landing. Never in this picture all the legs are completely stretched like this, right? And this motion is only possible if you have this kind of high resolution photography. Otherwise what you see is what you believe, right? So in chemistry also, if people say without regard for any of these insights that okay, there is a transition state structure evolving this, it's a plausible mechanism and all, you always have to be skeptical unless it is proven. Okay, so we just take this spirit forward and then see what in chemistry, so just not to give away our cats, because quantum mechanics love cats, quantum mechanicians love cats, right? Schrodinger's cat you have heard about, right? In the context of superposition, in explaining the superposition principle of quantum mechanics, Schrodinger cat was used, and quantum dynamicists like us would use also cat to prove something, that when you let the cat go from this from this position to the ground, it kind of takes all this route. If you observe, I mean, it happens in a fraction of a second. Okay, so we never get to see, right, because our the blink of an eye is less than a second, is around a second, I guess. So we cannot resolve this time scale. Yeah, so it happens much more faster. In doing so, it exhibits amazing physics. You know, it kind of conserves the angular momentum by kind of squeezing in the legs, and then and then uh, uh, and then I mean, so once you squeeze these legs, you're kind of reducing the moment of inertia, and then cat moves faster, so increasing the angular velocity. So it's I omega that has to be constant, right? And then once, so it kind of tilts. I mean, it's an amazing spine that these cats have. It kind of half tilts this way, and then the other half tilts the other way, so that there is no spinning motion. Okay, unless you have an external force, there is no spinning motion. There is no external force here, and then it brings all these things together, and then tries to conserve its angular momentum, and then slowly comes to this stage. You know, so this can be mapped by, mapped by 50 microsecond resolution. Camera. Okay. Okay, in chemistry, you probably know what happens from your Jablonski diagram: radiative decays, the time scales, fluorescence, phosphorescence, rotational motion. Okay, you probably have rotational motion, vibrational motion we were talking about, right? So these are the time scales associated with that. And then there is something called intramolecular vibrational distribution during the chemical reaction, because once you put in energy to, let's say when you supply temperature to the reactants, where does this energy go? Does it go to the bond where it is supposed to be delivered, or does it distribute over the entire molecule? So that's where, because the modes are kind of coupled with each other, right? So you are not actually putting the energy into one particular number. You are kind of trying to localize the energy in one bond. It's not a normal mode. The local bond is not a normal mode. And then this bond communicates with all other bonds. Then immediately the energy gets statistically distributed over the entire molecule. Okay, that happens in this femtosecond. 10 power minus 10, 11 seconds. So at femtosecond time scales, you kind of avoid this, right? Because you are kind of inputting the energy very fast and trying to observe it in very fast, and then it's okay. And then all other chemical, physical, biological changes and the time scale associated with it are here, and then our relevant time scales are here. And then these are the people that were awarded Nobel Prize for every, time duration down until 10 power minus 15 femtoseconds. Okay, that means when these guys, have you heard of stop flow method in kinetics? Stop flow method. So that's a Nobel Prize for this guy for developing this. Okay, and then have you heard of these guys, Eigen, Porter, in any context? No, not that Eigen. So these are all like, all these guys are awarded Nobel Prize for developing the technology to create laser pulses of various time duration, for instance. So he has created laser pulses of microseconds. This goes to femtosecond, and then recently also attosecond pulses were generated, and it was also awarded Nobel Prize. Okay. So every 3 orders of magnitude going down in time scale, you get a Nobel Prize. So 10 power minus 21 is the next, but we don't have, chemistry doesn't operate at that time scale. You don't have to worry. Okay. So fine. So this is the Nobel Prize poster of this guy, Ahmad Zivel, where he observed. You know Diels-Alder reaction, right? So this is just the reverse of the Diels-Alder reaction. So you have cyclobutane going to a transition state and then getting cleaved into two ethylenes, right? So they kind of used the initial I mean, they did not get to the cyclobutane. Okay, the reactant was not cyclobutane. It's kind of there is some CO group here, and then 4 carbons attached to it, attached one to another, and then to it. Yeah. And then the CO is cleaved, and you get an unstable intermediate, the kind of radical intermediate people call it. And then he observed from t equal to 0 time to t equal to some final time where the products are formed, all the steps involved in the mechanism of this reaction. You see here, it's kind of filmed successively, and then using this kind of laser setup, which you may not see it here now. And then he was awarded, it's like a molecular movie, no? It's like a molecular movie. So he was awarded for Nobel Prize for this and some other, in combination with some other works. Okay, this is how our life is. It's not simple Jablonski diagram with S0, S1, and then you separate the electronic states, and the electronic state here is coupled to the electronic state here, and coupled to the electronic state here, electronic state here. So you expect when you have a picture of this kind, you excite and then you expect it to fluoresce, right? But that may not happen because you see here, there, if let's say if you excite it to a blue surface, okay, it can go to green surface, and from green surface it can come back without emitting light and then back to its position. So that's how the fluorescence quenching and other things happen, and these happen on picosecond time scales. Okay, anyway, I mean, maybe we have seen that, right? And observing this using laser pulses is the motive here. Okay. Okay, you can clock, I mean, that's what he did. Zewell clocked his chemical reactions using femtosecond laser pulse. So he excited this molecule called ICN molecule. Okay, this is iodine atom CN. Okay, so there are 2 potential energy surfaces here: the ground state potential energy surface, the excited state potential energy surface, shown as a function of just R, but there is another coordinate here because it's a 2-dimensional surface, right? There is another coordinate here. It's kind of CN bending, ICN, the I, and there is a bond angle, right? So when you excite it to this surface, so it so happens that the iodine doesn't like carbon atom at all, it throws it away. That's called repulsive surface. Okay, it's like a rolling marble. Okay, on the surface. So these surfaces are called repulsive surfaces. So by the way, why should it go this way? Why not this way? Yeah. So you have a potential, right? You have a potential. Yeah. What is the force associated with this potential acting on the system? Have you heard of this negative gradient of the potential being the force? Yeah. So you see here, you have a potential. I mean, that's called central forces. You know, central forces are negative gradients of the potentials. Okay. So you have a potential here. The gradient is negative in this direction and positive in this direction. Do you agree? If you have a curve like this, what is the gradient associated with this curve here? Gradient means the slope. Is it negative or positive? It's negative. Here, negative. Here, here. Okay. So the force acts in this direction. That's the negative gradient of the potential. This direction. When the wave packet moves forward and then goes here with some momentum, and then the force again acts in this direction, it brings it back. Okay. That's what it does, oscillatory motion. So therefore here the potential is not bound, it's not bound to bring it back. So once you land your ICN on this top surface, It simply rushes towards this. So you are kind of creating a coherent wave packet. Now with the vibrational levels of this state, you have a wave packet and it's moving forward. And then when you are here, the ICN bond is broken within 200 femtoseconds. In 200 femtoseconds, right? So it has a intuitive appeal, right? How chemical bond is being broken here. And then this was locked. There is another reaction. You see here, NAI, which we were actually seeing in the morning. So NAI here is covalent. Okay. Sorry. At this configuration, it's ionic. Okay. And then when you excite it here, it has the because this is the surface associated with covalent bond. This is a surface associated with ionic bond. You bring Na plus plus I minus, you get this curve. You bring Na plus I atoms, you get this curve. That's the energy associated with that. Okay. So you kind of excite here. The wave packet oscillates back and forth because it's kind of now slightly bound, unlike this one. It's not a repulsive surface completely. As it moves back and forth, it kind of leaks some amount and goes this way. Because when it is here, it's like a conical intersection, no? In the multi-dimensional, it's a crossing point. It's like two paths available for this wave. So it actually has to go this way and then come back this way. When it is hitting this one, some of the wave packet is leaking and then going to this product. And then when it can go to that channel, you get Na plus I minus. Okay. So you see here. So this wave packet motion is clearly seen in the oscillations here. So it goes and comes back. So first you started with this NAI covalent, and then the wave packet. So what is calculated here is simply this. So it's kind of, you have a wave packet chi of t, and then you take the overlap with this one. That's what is calculated, and then square it. You understand? You solve that equation, you get chi of t. You know chi of 0 because that's where you landed this one. So you keep this fixed in the sense you have an initial wave packet at time t equal to 0. You let it go by that equation, and then again when it comes back, it tries to when it comes back, some of the wave packet has already leaked. The overlap actually decreases. Okay. Time to time it keeps decreasing as and when in 10 oscillations the whole NAI is actually branched into Na plus I and Na plus I minus. Both the ionic and covalent bonds are from. Somewhere here you find the transition state, somewhere here. So when it's actually somewhere here, you can kind of find the transition state. Okay. You see here the transition state. Yeah. So yeah, that's what this wave packet dynamics is actually. So in time it moves farther and comes back and then moves back. That's what is done. Okay. So from this figure, okay, you have an oscillatory motion here. I asked you one question. What is the vibrational period of NAI? You can get that, okay, from this figure, because you just have to identify the vibrational, the vibrational time period associated with it. Then you can calculate vibrational frequency, right? It's like it's the difference between these two peaks give you vibrational time period, which is, let's say, 1 picosecond, and then 1 over tau will give you the frequency, NAI frequency in this well. What is the rate of formation of Na atoms? So you can just fit these are like light induced absorption of Na atoms, free fragments, and then you can kind of get if you fit this curve to exponential rate, you get the time scale associated with this. You can get 1 over tau again as the rate of this dissociation, okay, rate of formation of Na. So you see from these two plots, these are experimental plots, you can deduce the mechanism underlying this reaction as well as the macroscopic kinetics that you usually write it, right? Okay, it's time product concentration times the product and things like this. You can just these plots, you can get how much time this wave packet spends in this well before getting cleaved into Na plus I or Na plus I. Where can you locate the optimal transition state, the possible transition state, and things like this. So this is done with pump probe setup. We don't have time. Just then you can see a movie just to appreciate how pump and probe setup is done. Okay. You have a molecular structure. Okay. A laser pulse comes and then creates a non-equilibrium situation. This is called probe pulse. Okay. Yeah, that's how you can probe the configurations. Once you create with pump pulse some non-stationary state, and then this non-stationary starts evolving, I mean different molecular configurations, and then you probe it time to time with a probe pulse. Okay, that's what is done. Then so this is how typical laser setup looks like. Looks with lot of electronics, optics in there. That's what he used. And then one application of this pump probe spectroscopy is to study the initial event of vision. You know, there is a what is that called, rhodopsin pigment. Okay, it's you have you heard of rhodopsin molecule? Yeah, what is this? What is this molecule? Yeah, so that's the one which actually receives the light. Okay, when it receives the light, so that lies somewhere here. The rhodopsin protein somewhere lies in the cones here. Okay, cones and rods, and then it is actually buried in this opsin protein. Okay, and then it is not a big molecule. It is small molecule with 11 cc bonds, I guess. Is it 11? Not sure, but there is this carbon-carbon double bond. So when it receives the light, this double bond has to tilt. It becomes cis becomes trans. Okay, that's the job it does, and then it kind of triggers a signal to the opsin protein and then to the brain nerves and all. That's how we see. Okay, and then it happens in 200 femtoseconds. Okay, this whole initial event of vision happens 200 femtoseconds, and then you can probe that event using pump probe technique. Okay, we don't have time, but you can probably see through any video or lecture, you can get it. Okay. Okay, fine. Yeah, that's how it goes. Okay. We did not touch the spectroscopic component of it. We only tried to do the justice to the dynamics component of it. But next time when we have time, we'll see that. Okay, fine. Okay.
SwayamPrabha. Digital India. Educated India.